Chapter 6, the nomenclature of inorganic compounds. And here we have a seashell, which is formed from calcium carbonate. That's its scientific name, but its common name is limestone. And this chapter deals with the system of naming things. If you go back a few hundred years ago, so few chemicals were known that it was reasonable to expect a chemist just to know the name of every single compound. So when you only have 200 to 300 compounds, you can memorize them all. But these days, over 16 million compounds are known, and therefore it's no longer possible to memorize a specific name for each one. And therefore, a system had to be developed that allowed people to name chemicals. And therefore, if you knew the system, as long as you understood how the system worked, you could name a chemical even if you had never seen it before. If you saw its structure, you would know what its name was. And if you heard the name of a chemical, even if you had never seen the structure, you would know what the structure was. And so that is the usefulness of a system, is that once you learn the system, you know how to name stuff. So here we have N2O. The systematic name is dinitrogen monoxide, and when a chemist sees that, they know that there's 2 nitrogens and 1 oxygen in that molecule, N2O. So if you told a chemist dinitrogen monoxide, they would write out N2O. The common name is nitrous oxide, or laughing gas, and if you say laughing gas, that doesn't tell you anything about the structure. And so common names are the historical names of compounds which are not based on any rules. And it's called laughing gas because if a person breathes a large dose of it, they will laugh hysterically. In small amounts, nitrous oxide is used by some dentist offices as a kind of a mild anesthesia, and it helps with dental procedures. But the systematic name is dinitrogen monoxide. There are 2 nitrogens for every oxygen. And so we're going to see the systematic system tells you a lot about the chemical itself. So common names reveal nothing about the physical and chemical properties of a compound. Calcium oxide. If you told a chemist calcium oxide, they would immediately draw CaO. However, the common name is lime. And again, that doesn't tell you anything about the chemical. So again, chemists prefer systematic names because this way, as long as someone understands the rules of naming something, even if they've never seen a compound before, if you say the name, they can figure out what it is. Or if they see the structure, they can figure out how to name it, and that's really useful. The system of nomenclature is devised by the International Union of Pure and Applied Chemistry. All chemists who are a member of their National Chemical Society, so in the U.S. it's the American Chemical Society, are able to become part of the International Union of Pure and Applied Chemistry. And this just has chemists from every country of the world, and they meet twice a year, and they just work out things like naming and stuff so that everyone is on the same page and can understand everyone else's work. So we will focus on the nomenclature of inorganic compounds in this class. And we covered naming elements in Chapter 3. And so here we're going to see binary compounds are any chemical compound that has 2 different elements present. If there's 3 or more elements present, now we have a polyatomic compound. So certain elements exist as polyatomic molecules. So nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, and iodine are the 7 diatomic molecules. So hydrogen is always found as H2, never H. Oxygen is always found as O2, never O. Nitrogen is always found as N2. Fluorine, always F2. Chlorine, always Cl2, never just one Cl. Bromine, always Br2. Iodine, always I2. And so you can find these elements pure, but they're always multiple atoms bound together in a single molecule. 2 other elements exist in polyatomic arrangements. Sulfur, there's always 8 atoms in a single molecule, and phosphorus, there's always 4 atoms in a molecule. A charged particle is an ion, and we produce ions by either gaining or losing electrons. We never mess with the nucleus in this class. And so for potassium atom to form the potassium ion, an atom of potassium has to lose 1 electron. And then you get the potassium ion, which is a cation. So again, we form cations by the atom losing electrons. We form anions by the atom gaining electrons. So magnesium loses 2 electrons. Aluminum loses 3 electrons. And in chapter 10, we'll show exactly why magnesium always loses 2 and why aluminum always loses 3, why sodium always loses 1. We will find that out in chapter 10. Naming these cations are pretty easy. Potassium atom becomes potassium ion. Magnesium atom becomes magnesium ion. Aluminum atom becomes aluminum ion. And so naming them is simple. For the anions, an atom gains an electron to become a negative anion. Chlorine gains 1 electron to become chloride. Oxygen gains 2 electrons to become oxide. And when we name the anions, you use the stem of the nonmetal, but then it gets an IDE ending. So fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. Oxygen becomes oxide. Nitrogen becomes nitride. Phosphorus would become phosphide. Sulfur becomes sulfide. Selenium becomes selenide. You get the IDE ending on a anion. And we can predict the ion charge from the periodic table. Group 1 always becomes +1 in this class. Hydrogen is a bit of an exception. You'll see hydrogen that has a -1 too, because hydrogen, the atom has 1 electron. If it gains 1 more electron, it becomes like helium, and so that's also stable. And so hydrogen is unique in that it can be +1 or -1 in this class. But all the other ones, lithium, sodium, potassium, rubidium, cesium, always +1, always. Group 2, beryllium, magnesium, calcium, strontium, barium, radium, always +2. Aluminum in group 3, always +3. The transition metals, their charges vary, so we'll cover them in a later section. But like copper can be +1 or +2, and so we're going to see you actually have to articulate and state what the charge is, because the charge can be multiple different things. Or chromium, it can be 1 through 6. There's lots of different charges on chromium. Group 5 will become -3. Nitride is -3. Phosphide is -3. Arsenide, -3. Group 6 is -2. Oxide is -2. Sulfide, selenide, -2. And group 7 is -1. Fluoride, chloride, bromide, and iodide. And then group 8, noble gases, charge is 0. They never form ions. For an ionic compound, the overall net charge has to be 0. And that's going to be the guiding factor here when we figure out what the charge should be. All the positives have to be neutralized by all the negatives. And that's how we're going to know how many of each we should have. So for example, sodium chloride. Sodium is +1, chloride is -1. They need to be in a 1-to-1 ratio to cancel out. Sodium bromide. Sodium is +1, bromide is -1. Need to be in a 1-to-1 ratio to cancel out. But potassium sulfide. Potassium is +1, sulfide is -2. We need 2 positive ones to neutralize our -2. So if we come down here, K2S. You need 2 positive ones to neutralize a -2. Zinc sulfate. Zinc is +2, sulfate is -2. They're in a 1-to-1 ratio. Ammonium phosphate. Ammonium is +1, phosphate is -3. We need 3 positive ones to neutralize a -3. And therefore, there are 3 ammoniums for every 1 phosphate. Aluminum chromate. Aluminum is +3, chromate is -2. The smallest number that 3 and 2 go into is 6. So we have 2 aluminums for +6 and 3 chromates for -6. Again, at the end, the compound has to be neutral. All the positives have to be canceled out by all the negatives. It has to be a neutral compound. So when we name them, we will write the metal ion formula followed by the nonmetal ion formula. And then we make sure that the numbers make sense so that the overall charge is 0. So barium nitride. Barium is +2. Nitride is -3. So the smallest number 2 and 3 go into is 6. We need 3 bariums for +6 and 2 nitrides for -6. And so this is a neutral compound. So you know that's the correct formula. So write the chemical formula for magnesium oxide. Magnesium is +2, oxide is -2. They'll be in a 1-to-1 ratio because that gives you a neutral compound. Binary compounds contain only 2 different elements. They can be either ionic or molecular. And if they're ionic, they can either be containing a metal that only has one possible charge, like sodium has to be +1. Potassium has to be +1. Magnesium has to be +2. Aluminum has to be +3. Or they can be a metal which has multiple cations, like iron can be +2 or +3. Tin can be +2 or +4. Lead can be +2 or +4. And they'll have 2 sets of rules there. So when we're naming binary compounds that contain a metal which only forms one cation, we first, by convention, write the cation and then the anion. So we name the cation, we write the anion root, and we add the "ide" suffix. So this would give us sodium bromide, sodium fluoride, sodium hydride. Again, this, as we talked about earlier, hydrogen can be -1. So hydride is when hydrogen is -1 charge. That's hydride. Nitrogen, sodium nitride. Oxygen becomes sodium oxide. They get the IDE endings. So name this compound. This would give us magnesium bromide. Sodium oxide. And again, magnesium is +2. Bromine is -1. We need 2 -1s to neutralize a +2. Sodium is +1. Oxide is -2. We need 2 +1s to neutralize a -2. Na2O. And again, the net guiding principle is the overall compound has to be electrically neutral. The positives and the negatives have to cancel out. So we name the compound Al2O3. That is aluminum oxide. And again, aluminum, 2 of them gives you 2 + 3s is +6. And oxide, 3 -2s gives you -6. So it is a neutral compound. That's correct. Calcium sulfide. Calcium's in group 2. It'll be +2. Sulfide's in group 6. It'll be -2. 1-to-1 ratio. BCAS. Neutral compound. If you get a neutral compound, you know it's correct.